All right. Um, well, good afternoon, everybody. How I wish I could do this in person, but the show must go on. I am thrilled and honored to be invited to speak at this forum today. And the talk today is really focused on my trials and tribulations, my attempts at trying to build trustworthy reinforcement learning using tools and techniques developed within the formal reasoning community. And as we go through this talk, I will invite you to decide for yourself whether formal reasoning in reinforcement learning is a boon or is it a bane. Starting right off the bat, reinforcement learning is considered the third pillar of machine learning. There is supervised learning, there is unsupervised learning, and then there is reinforcement learning. The problem of reinforcement learning is to generate a policy for a given task. In that sense, reinforcement learning is really a synthesis algorithm. The defining feature here is that the environment in which the policy should operate in is assumed to be unknown. So this policy has to be generated by only sampling the environment. You should think of a reinforcement learning algorithm as this policy iteration loop in which the policy samples the environment. Based on this sample, the environment returns a feedback to the policy, and then the policy uses the feedback to improve itself. And this cycle of interaction continues until the policy can't be improved any further. Reinforcement learning is a very general framework and it has wide ranging applications. For example, in the sphere of robotics or autonomous vehicles, reinforcement learning has been used to design control policies. RL is particularly suited in these setups because in the real world, modeling the real world is extremely hard. So one might as well assume that the environment is unknown. For similar reasons, RL finds applications in medical diagnostics and also in finance. And closer to home in program analysis, RL has been used to solve computationally hard problems such as invariant generation and bug finding. Now, traditionally in RL, the task for which we want to generate a policy is expressed in the form of a reward function. Now, I argue that this could be quite challenging. For example, suppose the task was something simple. Suppose the task was to reach P. Then the corresponding reward function is actually quite simple. The reward function can simply return 1 once it reaches P and return 0 otherwise. But suppose the task is a little bit more complex, and now the task is to reach P and then reach Q. Observe, we can't simply compose the reward function for reach P with the reward function of reach Q. Because if we did that, we would not be able to eradicate wrong behaviors which reach Q without ever visiting P. Now, you may be thinking that there is some reward function that correctly corresponds even to this slightly more complex task, and you are right in thinking that. But designing such a reward function would require a little bit more effort. And as the tasks become more complex, as they become longer and longer, or as logical constraints appear in the tasks, writing a reward function becomes cumbersome. An alternate for task specifications is temporal logics. Temporal logics are great at describing properties over long executions. Over the past many years, several temporal logics have been defined, and they have the inherent quality of being able to encode logical constraints as well as temporal constraints. The real benefit temporal logics enjoy over rewards is that their syntax is very close to natural language, and therefore they simplify the task of task specification. For instance, reach P is simply written as eventually P, and reach P then reach Q simply composes eventually P and eventually Q. So it's not surprising that an emerging area of research in the last 5 years or so has been to design reinforcement learning algorithms where the task is specified using temporal logic and not reward functions. But I argue, and this is the point of where we come in with formal reasoning background, that temporal specifications offer much more than simply being an easier way to specify task. Temporal logics have several properties that could be extrapolated, that could be leveraged in order to design better reinforcement learning algorithms. For example, temporal specifications have a clean and rigorous semantics. And we know how useful this property has been to designing trustworthy computing for hardware and software systems. So the hope is that by using temporal logics, we will be able to design reinforcement learning algorithms that are testable, that can be verified, and that are interpretable, and so on. All of these are desirable qualities for a reinforcement learning algorithm. So the hope is that the properties of temporal specifications could be used to design algorithms with desirable properties. However, the slate is not so straightforward. Temporal specifications also have certain properties that could inhibit this development. For example, temporal specifications are known to be non-robust, meaning small changes in the system could drastically change the outcome of the satisfaction of a temporal logic. Now, this could be particularly harmful in reinforcement learning, where the nature of learning policies is by small changes. So as the policies learned over small changes, non-robustness of temporal specifications could actually threat the design of reinforcement learning algorithms with desirable properties. So it is this friction between the good properties of temporal specifications and the negative properties of temporal specifications that get more pronounced in reinforcement learning that leads us to the question of whether learning from temporal specifications is a boon or is it a bane. During the course of this talk, I will present several cases for you to make your decision on what side of this debate you fall on. For the time being, we can agree that temporal specifications are easier to specify tasks than they are for rewards. The two other axes we will discuss are theoretical guarantees and algorithmic performance of reinforcement learning from rewards versus reinforcement learning from temporal specifications. So let's start by talking about the traditional reinforcement learning problem and what theoretical guarantees and how their algorithms perform. So let's formalize the problem of RL in the traditional setting. The environment in RL is encoded by a Markov decision process, an MDP. An MDP consists of states S and actions A. Observe that we do not restrict ourselves to where either S or A is a finite set. We could be in a continuous MDP where the number of states and the number of actions could be infinite. There is also a transition probability function which assigns a probability on transitions in the MDP. And finally, there is an initial state distribution which informs us what all states, the states with support 0, are ones where executions could start from in the environment. For example, here is a 9 rooms environment. This is a continuous state MDP with an infinite number of states and an infinite number of actions. States are given by coordinates in the Cartesian plane of reals. So every coordinate xy is a state. Actions are given by theta d, where theta is an angle and d is the displacement. The transition probability of such transitions is high when the target state is correctly calculated from the source state and the action. And with very small probability, actions might fail and transitions may go into an error state. And finally, the initial state distribution or the support in this environment is given by the blue region as 0. So there could be multiple initial states. And in this case, there are an infinite number of initial states. Finally, a policy is simply a map from a finite history of execution to a distribution on what action to take next. Really, a policy is simply a recipe that informs the learning agent on how to act in the environment in order to achieve its objective. Now, the reinforcement learning problem is defined as follows. Given an MDP and given a task expressed in the form of a reward function, assuming transition probabilities in the MDP are unknown, can we generate a policy that optimizes the total reward? We don't need to get into the details of what a reward function is, what the discount factor is, or what expected discounted sum reward is. For the purpose of this talk, it is sufficient to know that the reward function encodes the desired task, and we are trying to generate a policy that optimizes that task. Now, if the transition probabilities were known, then this problem might sound familiar. If the transition probabilities are known, then the problem of finding the optimal policy is simply the optimization problem on MDPs. Optimization problem on MDPs is one of the most fundamental problems, and in fact, it has been studied for more than half a century. A lot is known about optimization algorithms, about their theoretical guarantees, about their practical performance, but for our purpose, it is sufficient to know that in an MDP, it is known that there exists an optimal policy which is both memoryless and deterministic, and because of this, the optimal policy can be found by simply solving the Bellman equations. The Bellman equations simply give us a score for every state, which is the expectation of score of all of the neighboring states. And observe in this formulation that it is crucial to know the the transition probabilities. P is a crucial ingredient to being able to solve Bellman equations. And it is this that in reinforcement learning, when the transition probabilities are unknown, we cannot set up the Bellman equations, so we cannot use the algorithms known for optimization in MDP. To compensate for the lack of transition probabilities, we assume access to a simulator of the MDP. The simulator really is the simulator of the MDP assumes that at every stage, we know what the current state in the MDP is. The simulator also provides two functions. It provides two APIs. The first API simply says that no matter what state we are in, we can always reset ourselves to one of the initial states. And the second API simply lets us sample actions. So we sample an action, and based on that action, the current state gets updated. The importance of these two APIs is that these are sufficient to sample multiple executions in the MDP. And sampling executions in the MDP is crucial to the design of reinforcement learning algorithms. In particular, algorithms for reinforcement learning are sampling based. At a very high level, the idea is that by sampling lots of executions, we can estimate what the transition probabilities are. And once we have a good enough estimate of the transition probabilities, we could set up the Bellman equations in order to find the optimal policy. These algorithms are also known to have theoretical guarantees. Note that the theoretical guarantees are limited to MDPs with finitely many states and do not extend to MDPs with an infinite number of states. I will not describe what these guarantees mean formally, but only give you an intuitive sense of what these guarantees are. So reinforcement learning algorithms are known to have asymptotic guarantees, which means that if you could sample an infinite number of times, that is, if you could sample an infinite number of executions, then these algorithms are guaranteed to converge to the optimal policy. The other kind of guarantee these algorithms have are called pack guarantees, which says that if you could sample a finite number of times, then with very high confidence, you would converge to a near optimal policy. These are important because simply by running these algorithms, they give us the confidence of learning a policy which is either near optimal or optimal with respect to the rewards. So to return to our table, reinforcement learning from rewards, which is the traditional reinforcement learning problem, has theoretical guarantees of having asymptoticity and pack. Empirically, these algorithms are also known to have extremely good performance for short horizon tasks. However, it has been shown that their performance in long horizon tasks is extremely poor. So our question is, does reinforcement learning from temporal specifications have similar properties for theoretical guarantees and algorithmic performance, or are they worse? So let's start by defining what reinforcement learning from temporal specifications is. it's actually the same problem. So we are given an MDP, but now the task is expressed using a temporal specification and not a reward function. So given an MDP and a temporal logic specification, once again, assuming transition probabilities are unknown, can we generate a policy that optimizes probability of satisfaction of the temporal specification? Once again, observe, if the transition probabilities were known, then this is simply the problem of probabilistic model checking, for which there is a lot of literature already, but the learning problem kicks in only when transition probabilities are unknown. So we assume a simulator is provided, so we can sample executions, and simply by sampling executions, can we find the optimal policy. As an example, let's go back to our 9 rooms environment. Suppose the specification is to eventually reach S1. Recall that S0 is the support of the initial state distribution. Then the optimal policy is any policy that will be able to create the dotted line in the illustration. So let's see what can we say about theoretical guarantees of learning from specifications. Let's start with a really simple example. So here we have a 3-state MDP. There is the initial state, there is a state called safe and an unsafe state. In this case, there is only one initial state, which is init. And the actions from init are either A or B. From init, if you take the action A, with probability 1, you will go to the safe state. From init, if you take action B, then with 1 minus gamma probability, you will go to the safe state. But with a gamma probability, you will end up in the unsafe state. And suppose safe and unsafe states are sinks. So from there on, every execution remains in those states. Now suppose our specification is to avoid the unsafe state. Then the optimal policy corresponding to this specification is clearly to take action A from init. Observe, if you take action B from init, then there is a probability with which you would go to the unsafe state, and therefore the probability of satisfaction of specification would be lower. But if you take action A, then the probability of satisfaction is exactly equal to 1. And that is the optimal policy. Now for theoretical guarantees, let us ask the following question. Can I learn the optimal policy using a finite number of samples? All right? So let's go over this gradually. Suppose I can sample k number of times, where k is some function in the size of inputs. Right? We don't need to get into what these inputs are. Just take k is some finite number. Now, the only thing, or one of the more important things that we need to be able to infer by sampling is to not take action B. Because if we take action B, there is a chance that you end up in the unsafe state. So let's take the most optimistic case, where from the initial state, the algorithm only samples action B. So from init, we have sampled action B k number of times. Now observe that if gamma was extremely small, if the probability of reaching the unsafe state was extremely small, it is possible that even after sampling k number of times, the algorithm will never discover that there is an edge from init to safe. So if the unsafe transition is extremely rare, then even after sampling a finite number of times, you may never discover that unsafe edge. And if we don't discover the unsafe edge, the algorithm might learn that the optimal policy is to take action B. Clearly, this is not the optimal policy. And now observe that no matter what we have argued is that no matter how many finite number of samples you take, there can always be a gamma small enough that will necessarily lead to learning a suboptimal policy. So we cannot learn an optimal policy in finite number of steps when the specification is a temporal logic. In fact, we show we prove a much stronger result. And we prove that not only can we not learn optimal policies, we cannot learn a near optimal policy by sampling a finite number of times. I'm not getting into the formal definition of what a pack algorithm is, but intuitively, we cannot learn near optimal in finite number of samples with high confidence. So this feels like, in terms of theoretical guarantees, learning from temporal specifications has a clear disadvantage. In practice, pack is the kind of guarantee we require, because in practice, we can only sample a finite number of times. So if we don't have pack, we have no theoretical guarantees by learning from temporal specifications. So let's switch gears and talk about algorithmic performance. Does learning from temporal specifications offer better algorithmic performance? In particular, is the algorithmic performance on long horizon tasks better than learning from rewards? Let's start with a simple example. Going back to the 9 rooms environment, here S0 is the support of the initial state distribution. O is an obstacle that needs to be avoided at all times. The gray boxes S1, S2, and S3 are 3 different regions in the environment. And suppose our specification says that visit either S1 or S2 and then visit S3 while avoiding O. Now observe this, the specification is clearly realizable. In fact, the optimal policy would be one which is able to navigate from S0 to S1 to S3 while navigating around the obstacle O so that it doesn't hit into it. So for this specification, there exists an optimal policy, and the optimal policy is as illustrated in the diagram. Now, given the lack of theoretical guarantees, performance of algorithms is evaluated empirically. So on the x-axis, we will plot the number of samples, and on the y-axis, we will plot the probability with which the policy has satisfied the specification given an x number of samples. Since the y-axis is a probability, it only ranges from 0 to 1. So the ideal curve, the best curve, or the best algorithm would be one where the curve starts at 0 probability at 0 number of samples, and very quickly, by sampling very few times, it is able to learn a policy that satisfies with high probability. Ideally, we want the probability of the ultimate policy to be 1, but as long as the algorithm is able to learn high quality policy within few number of samples, that is the kind of algorithm we want. That is the kind of performance we want from our algorithms. So let's look at how state-of-the-art algorithms that learn from specifications fare on this benchmark with this given specification. And here is what we observe. Once again, x-axis is number of samples, y-axis is probability. If you're wondering where the plots are, look more closely. They're all touching the x-axis. Now this is terribly bad news, because what this plot shows is that even after sampling a few million of times, these algorithms learn policies that satisfy the specification with negligible probability. The reason this happens is because state-of-the-art algorithms convert the problem of learning from specifications to a problem of learning from rewards. And we know that learning from rewards fares extremely poorly on long horizon specifications, and that reflects in the performance of learning from temporal logic as well. Fortunately, in our work, we have been able to remedy this situation. In our work, we have proposed a new algorithm, DIRL, by which we show a DIRL that significantly improves the performance of learning from temporal logic. So on the same benchmark, the 9 rooms benchmark with the same specification, while state-of-the-art algorithms, the best they could do was learn a policy with negligible probability, our algorithm DIRL is able to learn high-quality policy within a few number of samples. And the way we do it is by leveraging the specification itself. Let me get into the details of how we do this. The key is to address the inherent myopia of reinforcement learning algorithms. Recall that RL is very good at learning short horizon tasks, but is very poor at learning long horizon tasks. We need to address this myopia. Let us illustrate this through an example. We have the same environment. It's a 9 rooms environment. S0 is the support of the initial state. S1, S2, S3 are 3 different regions, and O is an obstacle that needs to be avoided. Suppose the task is a short horizon task. The task is to visit S1 or S2 while avoiding 0. Now, for this short horizon specification, we can see that state-of-the-art algorithms actually perform very well. But recall that if we added one more aspect to the specification and said from S0 after visiting S1, S2, visit S3, then recall how all existing algorithms diminished in performance. The reason this happens is that in the first case, the learning algorithm learned how to visit S2 from S0. The reason it did this is because there is no obstacle from S0 to S2, and therefore it is the easier task to learn. In the second case, the same begins to happen. However, learning how to reach S2 is futile because there is no direct path from S2 to S3. What we need the learning algorithm to realize is that although it might be harder to learn S0 to S1 in the short run, in the long run satisfaction of the specification, that is the better policy to learn. So what these algorithms are missing is a high-level planning which informs the learning algorithm of the long horizon goal of the specification. And that's exactly what we incorporate in our algorithm DIRL by leveraging the structure of the specification. The specification we use is called spectral. It consists of temporal operators like eventually, always, and sequencing, and logical operators OR. We will not go into the syntax of the specification language, but it is sufficient to know that this specification language encodes reachability and safety tasks and their combinations. What we show is that every spectral specification can be used to obtain a DAG-like abstraction of the environment. This abstraction is constructed purely from the specification and does not need to know what the MDP is. So we are not violating the assumptions of reinforcement learning by constructing this DAG. In the case of the specification that visits S1 or S2 and then S3 while avoiding O, the corresponding DAG is shown on the slide, where S0 is the initial state of the DAG, S1, S2, S3 are other states, and S3 is the final state in the DAG. This DAG has 2 crucial properties. The first property is that every edge of this DAG corresponds to a subtask. So the edge from Si to Sj either corresponds to the subtask to reach Sj from Si, or it corresponds to the subtask to reach Sj from Si while maintaining some safety guarantees. So every edge is a subtask, and the subtask is strictly simpler than the original specification. The second property is that any real path, any real execution in the MDP, which is able to traverse from the initial state to the final state of the DAG, is guaranteed to satisfy the specification. Now, these 2 properties give rise to a natural compositional approach to learning, in which we use the first property to decompose the problem into several smaller problems, and the second property to compose the simpler problems into the final original problem. So in the decomposition phase, we say if every edge is a subtask and every subtask is a short horizon task, then we can use state-of-the-art algorithms to learn policies. So we can learn a policy for every edge. And then in the composition phase, we say, well, once we know policies for every edge, we want to find the best policy from initial to the final state. Now, the best policy is with respect to the probability with which the original specification is satisfied. A priori, we do not know probabilities on edges, but once the policies are learned in the first phase, we can use those policies to estimate probability along every edge. And once we have probability along every edge, we can simply find the path from initial to final state with the maximum probability, and that would be our optimal policy. To go through this example, in this case, the optimal policy would be one which goes from S0 to S1 to S3. And this would be optimal because the probability of success from S2 to S3 by pi4 would be extremely small. It would be negligible. So the overall path with maximum probability would be from S0 to S1 to S3. Now there is one. So far, the algorithm is rather straightforward. You decompose based on the abstraction, solve or learn for each subpolicy, and then compose once again using the abstraction. But there is one crucial detail in this algorithm, and that crucial detail has to do with how to learn a policy for every edge. Observe that suppose we were to try to learn the policy from S1 to S3, we need to know executions that start in S1. As part of the input simulator, the simulator for the original MDP, we only know how to start executions from S0. We don't know how to start executions from an intermediate state like S1 or S2. And without knowing how to start executions in S1 or S2, we can't learn policies that begin in those states. So, in addition to learning what edge policies are, we also need to learn initial state distributions for intermediate states in the DAG. Now, once again, we are able to learn an initial state distribution by exploiting the structure of the DAG. The idea is that for any intermediate state, we can induce an initial state distribution. And the way to do it is to say, well, if we know all policies along all paths from initial state to this intermediate state, then we can use those policies to induce a state distribution. Recall that this is a DAG, so there are only a finite number of paths from the initial state to any intermediate state. So this process is certainly going to terminate. However, finite could mean an exponential number of paths. So if we are smart about the order in which we learn edge policies and learn state distributions, we are able to show that we can learn state distributions and edge policies by sweeping the DAG exactly once. In other words, we visit every edge in the DAG exactly once in order to learn or in order to complete the compositional algorithm. In theory, what we say is that every edge is visited at most once, every edge is learned exactly once, so the number of reinforcement learning calls is exactly equal to as many edges there are. And finally, the size of the DAG is also small in the size of the specification, so overall, this algorithm is efficient. This algorithm is also extremely scalable. So here we have a 16 rooms environment. It is similar to the 9 rooms environment, except that it is larger and has 16 rooms. As earlier, the red boxes denote obstacles. I will use the shorthand box x to y to denote the specification from x, visit either the corner C1 or the corner C2, and then go to y while avoiding any obstacle on the way. Then, as earlier, then suppose A is the initial state distribution of the MDP. Then suppose the specification is box A to B. Then once again on this plot, X is the number of samples, Y is the probability with which learned policy satisfies specification after X number of samples. Once again, the higher the curve, the closer it is to the y-axis, the better the curve. DIRL is shown by the dotted blue line. You can see that when the specification is box A to B, DIRL is the best performing tool. We can make the specification longer and say that the specification is box A to B and then box B to C. Once again, DIRL is the best performing tool. But observe one more thing, that in comparison to the shorter specification box A to B and the longer specification box A to B and then box B to C, the performance of DIRL is somewhat similar. It is unaffected by the size of the specification. But if you look at the performance of the second best tool, demonstrated in green, we can see that as the specification becomes longer, the performance of the competing baselines reduces significantly. And this trend continues even as we make the specification longer and longer. So not only does DIRL scale to very long specifications, its performance is not affected much by the length of the specification. DIRL also scales very well in complex environments, in high-dimensional environments. We evaluated DIRL in open source on standard state-of-the-art benchmarks provided by open source tools such as OpenAI Gym. Here is the benchmark for the Baxter robotic arm. It is an industrial scale and an academic level benchmark. And we see that even in such environments, DIRL is the only tool that is able to learn anything reasonable. But let's talk about one more thing. In addition to efficiency and scalability, I claim algorithms like DIRL can contribute to verifiability of the learning algorithm. The critical aspect here is to realize that the policies that DIRL generates are composable. So instead of learning one really large neural network for a really long policy, we have learned smaller neural networks for relatively simple policies. And now the hope would be that as verification techniques for neural networks improve, we will be able to design compositional algorithms for verification that could give us some confidence, some formal guarantees about the correctness of the specifications we generate. So this, and in fact, there is recent work on compositional verification of policies enabled by reinforcement learning, and I envision these kinds of works to appear more often and be of extreme utility in showing verifying the algorithms, the policies learned. So going back to this, so now we have laid out all our cards. In terms of theoretical guarantees, rewards give asymptotic and PAC guarantees, but temporal specifications do not give PAC. In the terms of algorithmic performance, rewards don't perform well on long horizon tasks, temporal specifications scale very well, and the compositional aspect of our algorithm opens the possibility of verification of the generated policies. So here is the final, here is where all our cards are laid out. And now let me make my case for whether reinforcement learning from temporal specifications is a boon or a bane. And my case, my claim, is that based on this, learning from temporal specifications is indeed a boon. In terms of algorithmic performance, the fact that we have a temporal logic provides a structure and desirable properties that can improve the learning algorithm. In today's talk, I demonstrated that we could make reinforcement learning algorithms that are compositional, and these algorithms could be verified as well. Observe that compositionality and verifiability do not come easy in machine learning algorithms. To the best of our knowledge, there are no algorithms in reinforcement learning that are either compositional or verifiable. So just this already is a win in the favor of learning from temporal specifications to be a boon. Moving ahead or looking ahead, one can think about leveraging the structure of temporal logics to design algorithms with other desirable properties. For example, temporal specifications are inherently interpretable. Rewards are not interpretable at all. Temporal logic specifications are inherently generalizable. Rewards are not generalizable at all. And the hope is that because temporal logics are interpretable and generalizable, we will be able to, we can envision designing learning algorithms that also have these desirable properties. And all of this is possible simply because temporal logics have a structure, they have desirable properties, and those can be leveraged towards principal development of reinforcement learning algorithms that are more trustable. But let's address the elephant in the room. What about theoretical guarantees? And I argue it's not a big deal. The theoretical guarantees that one were getting from rewards applies only to finite state MDPs. In practice, MDPs are not finite state, they are continuous. So in practice, these guarantees do not hold either for reinforcement, even when learning from rewards. So it doesn't seem like lack of theoretical guarantees has any practical implication. But perhaps it hints at a bigger point here. When we talk about guarantees, we use our formal reasoning, we use the ideas of correctness that have been developed in hardware and software development. These notions of correctness are perhaps too obsolete for AI systems, which are far more complex than hardware and software systems. So perhaps the bigger point here is that in order to get guarantees from AI system, the bigger question is, and the bigger question for this community is to identify what it means to have meaningful guarantees for AI systems so that the AI and machine learning communities also appreciate the kinds of guarantees we offer. If you want to learn more about these algorithms, then we are presenting a tutorial on this at AAAI 23. If you're interested, please tune in, and we can talk more about the details about these algorithms. And last but not the least, I am starting at Georgia Tech very soon, and I'm looking to build my group. If you know of students who would be interested in working in these areas, please ask them to apply. The deadline is on December 13, so ask them to act promptly. So, my final words are in the debate of learning from temporal specifications. I believe it is a boon. What we have seen so far is promise enough to keep pursuing this direction. And with that, I open the floor to your judgment on whether it's a boon or bane. So please share your comments, thoughts, and questions on this. Thank you.
Hi, thanks for the cool talk. So it seems like when you're getting these induced distributions for the nodes further down in the graph, that the distribution that you get depends on the path that you took to get there. And that if you take a different path, you get a different induced distribution. So how do you deal with this? This seems like it might undermine some of the compositionality and verification things you're trying to do.
Yeah, thanks for the question. That's actually a very critical point. Because there are multiple paths, there could be multiple distributions that get induced. So the way we go about it is to say that inducing, we really have a heuristic. So it is quite difficult to find the best state distribution for intermediate states. So we simply use a heuristic based on the current application. So for example, the problem I showed today, which is learning for a single agent RL. In these cases, we simply say, look at the path with the best probability of satisfaction so far, right? And then we use only that path to induce a state distribution. However, we also observed that when we were trying to learn in multi-agent systems, then using the best was resulting in extremely poor performances. So in that case, we used the average along all paths. So long answer short, what heuristic to use to induce state distribution really depends on the application. In our experience in single agent RL, the best path is sufficient, and in multi-agent RL, doing an average of all paths worked well.
Thank you. In your notion of compositionality, it sounds like you are talking about sequential compositionality. Do you think that it is feasible to do a parallel composition?
There is a little bit of parallelism, right? Because of the or operator. For example, the example I had was choose between S1 or S2. So there is parallel compositionality in that sense. Does that answer your question?
Partly. It feels like, for example, when you say, well, I want to go to S1, then to S3, first you're going to go for the first objective and then the second one, while
Yeah.
if you composed it into two almost independent objectives, then you could actually try to solve them together.
Yeah, I mean that would be that would be great if one could. But the issue is that if we were trying, suppose take that example, right? S0 to S1 to S3. The issue is that we can't learn from S1 until we are able to induce a state distribution on it. Right? That's the bottleneck. So we need to be able to learn some things about all the paths before it to be able to learn anything starting from S1. So the bottleneck is really this reason that we don't have state distributions for intermediate states in the DAG. If there was a way to learn that without having to learn everything before, then perhaps we could make these algorithms much more parallel. And that in fact would be a great future direction.
Thanks.
Thanks for the great talk. I had a few questions. First, I guess you are dealing with finite state spaces still, or are you also dealing with deep case, for example, deep reinforcement learning, so on?
Yeah, so for all of the algorithmic performance, all of the benchmarks were continuous state MDPs, and the policy is represented by a neural network.
Okay.
Right, so
And
the line environment is continuous state. Baxter robotic arm is continuous state. Both of them are.
And like you did not set up your problem as like a multi-agent RL. It's still single state. Like the agent is made up of 4 different parts, but it's a single state, a single agent. It's not
Yes,
multi-agent. Okay.
yes. So the way the problems I showed in today's talk, all of them, the full state, the full dimensionality of the environment is considered as one agent. But in other work, we have multi-agent setup, but the multi-agent comes from the fact that there are multiple agents. But even there, every agent, the environment dimensionality of every agent is completely individual. We do not break that.
Okay. The last thing I wanted to ask was that let's suppose in many cases you don't have access to a simulator. Uh, let's say in medical environment, you usually only have an offline data set sometimes, and you want to learn something from that. Is there any hope in that direction? Because it's a harder task than just like learning from a simulator.
Right. I mean, it's certainly a harder task to learn only from a given. So, one of the benefits of collecting samples on the fly in reinforcement learning is that you can sample the next execution based on the best policy you've learned so far. In the problem setup that you're defining, where executions are given a priori, we can't make use of that. We can't make use of that online reasoning. So, it's certainly a much harder problem, and I don't think reinforcement learning would be the right way to go about it. To me, it seems like some form of supervised learning or unsupervised learning should be sufficient. But really, it's open to debate. I,
Okay.
I
Thank
don't
you.
have a clear view on. To me, it feels like if all of the data is present a priori, then using reinforcement learning is actually not reinforcement learning is not the right algorithm of choice.
Okay.
So I was really curious, what is the meaning of a node in this graph? Is it always an eventually proposition? Is it always some sort of atomic temporal proposition? Is it any proposition? What is the semantics?
Right. So the semantics of every node is derived from the specification itself. So it could be, it's really some predicate. right? So whatever predicates are present in the specification will appear, some Boolean combination of them is what every state denotes. And in terms of what they mean in the MDP, it's simply a collection of states in the MDP, right? And we do not require that these, for different nodes, these states be disjointed. They could overlap.
Okay, this was great. Let's thank the speaker once again for this great talk. I hope you could hear the applause.
Yes, thank you very much for the questions and for your attention. I wish this could be done in person, but I hope you have a great splash.
We did, and we wish the same.
Yes, and if there are further questions, please feel free to send me an email.